welcome to what is our fourth session at GSE this year. And we've got Israel Gross, who hasn't flown from America and is sitting in Jersey at his desktop. And he's going to be telling us about debugging and in particular kick storage violations. And I'm sure everyone's interested to know how that will go. So take it away, Israel. Thank you.
I would love to, except I can't find the screen share button. It disappeared on me.
Oh, excellent.
Did you take away screen sharing from me? Oh, there it is. I got it. Got it. It's
No,
showing
I didn't.
up now. Now it's there. Now it's there. Can you see my screen?
Yeah.
Good. Let's go into presentation mode for now. But I'm going to flip in and out of presentation mode because I have a couple screens to show. Well, good morning or good afternoon or good evening, depending on where you are in the world. I'm Israel Gross with Rocket Software. I'm a principal solutions advisor, whatever that means, but I specialize in Kix pretty much, and the Kix tooling like Kix Performance Analyzer and Configuration Manager and other Kix tools for Rocket. This morning, I'm going to talk about debugging Kix storage violations using IPCS, and it's hopefully a good agenda for you, because I looked at it and I've seen storage violation presentations over the years, and I'll be honest with you, you could find various different ones that don't even look similar to one another. And I always found there were certain bits and pieces I didn't like that were missing. So I wrote my own. So this is what I plan to cover today, right? I'm going to go through Kix storage management. I think it's important to understand how Kix manages storage if you want to be able to debug storage violations. And then we'll talk about what is a storage violation itself, right? Because obviously it's a unique concept to Kix. Not every product in the world has storage violations, and there are reasons for it. Obviously, the way Kix manages storage leaves it susceptible to storage violations, but of course, that's why Kix runs so quickly. I'll talk a few items about causes of storage violations, just so you get a feel for how easy it is to actually violate storage in the world of Kix. And then some protection options, right? So Kix provides lots of protection for storage violations. You can't protect against all storage violations, right? Nobody will stop you from shooting yourself in the foot, right? You'll be able to violate all the storage that you own. But other than that, you can protect for most other storage violations, and that's what I'm going to show you. Then we'll do a little bit on storage manager internals, right? So in order to solve storage violations, you have to be able to go through a particular dump, right? And look at certain control blocks within Kix to see what storage areas are violated. So I'm going to talk about how you'd solve one of these things, and you're going to see one of the ways to solve it is, of course, understanding what the violated area looks like. So maybe you recognize the data in the violation itself, and in order to do that, you have to be able to chain up to the data inside of a dump, and you have to know a little bit about internals. And then I have about 6 foils at the end of this presentation that we're going to go back and forth using a live dump, where we're actually going to take a look at the storage violation. We may or may not solve it. That's not really as important to me, because as sysprogs, it's more important to actually find the violated area, see if you could determine what program could have caused the violation, and then hand it off, obviously, to an applications person. If you happen to be the applications person, we can give you some advice as to how to solve some of those problems. So that's what we're going to do. Let's start with Kix storage management. So you guys can hear me okay? Everything's okay, right? Just double checking with you, Rob.
Yeah, everything's fine.
Okay, good. So in terms of Kix storage management, what does a Kix address space look like? So over the years, if you take a look, Kix started out with a 16 meg address space, right? So that's why we have the 16 megabyte line, and we ran our regions in 16 meg, and we had to run tons and tons of regions to support the amount of space we needed. And then we were able to run regions above the line, right? So our address spaces turned out to be 2 gigabytes, right? Which is where we are today. So we have a line where we go above and below that line. And we're going to talk about, obviously, the parameters you set to determine how much storage you allow Kix applications to use. But recently, within the last couple of releases, IBM has gone to 64-bit addressing on our mainframes, and therefore CICS supports that. A 64-bit address space is 8 billion times the size of one of our 2 gigabyte address spaces. Although, of course, keep in mind, we don't have that much real storage in the physical machine itself. It's 16 hexabytes, if you want a little trivia there. And to set that parameter, there's a parameter within CICS, a set parameter called memlimit, right? So we're going to talk a little bit about memlimit. And this presentation is not going to deal as much with above the bar, but I have to include it because that's where CICS will have some as well. And so we're probably familiar with setting a region size for the overall CICS region. I tend to run with region 0, which means that if I don't have an IEF UC exit to lower the amount, I can use up to the entire 2 gigabytes for my CICS region storage. And then you could set a mem limit. We'll talk about what to set it at and what it gets if you don't set it. But come on. Would help if my page turned. You guys there? Sorry, for some reason my machine wouldn't go down a page. Can you still see it, Rob?
I'm looking at 64 GSA equals mem limit at the top of your screen. CICS storage management, next storage.
Yeah, it should have gone to the next page. Do you see CICS dynamic storage area yet? Colorful page?
Yeah.
Okay, good. I'll use the page number next time. It's in the bottom right. So effectively, when CICS manages storage, right, depending on whether you code memlimit to limit the amount of storage above the bar, or EDSA lim or DSA lim, you're actually letting CICS know how much storage it can use internally for applications versus some of the system stuff behind the scenes, right? Now, within those areas, above the bar, above the line, and below the line, right, in the EDSA limit, we're broken up into individual pieces, right? So we're going to see that we have something called a dynamic storage area, or a DSA, and you have several DSAs below the line, above the line, and above the bar, where CICS actually allocates storage for application use, for system use. So the first thing you have to do is make sure you set the proper mem limit. You'll see in the note that it says it must be at least 10 gigabytes, right? Or CICS won't come up. For EDSA lim, which is the 31-bit storage size, or DSA lim, you get to set those values. The defaults are 800 meg above the line and 5 meg below the line. I think I've seen DSA limit below the line up to about 10 meg. Most people can't get it much higher than that, right? Because there's a bunch of system stuff down there anyway. So this is from a CICS region, CEMT, Inquire, DSA, and you'll see it gives you some information about SOS above the bar, above the line, or below the line. So you'll see I'm not at short on storage in any location there. And then you could see my DSA lim, what I have it set to, and then you could see the individual DSA sizes. So that was what I was saying earlier, right? When we have to look at storage within CICS, we have to know within which DSA it runs. So there's 4 DSAs, and this is CICS version 5.6. There are 4 DSAs below the line. There are 5 DSAs above the line, and there are 3 DSAs above the bar. You'll also notice that mem limit says no limit, right? If I run my region with region 0 when I start it up and I don't code a mem limit, the mem limit becomes no limit, right? And so that serves my purposes. So I have no restriction on my mem limit. You need at least 10 gig, as we mentioned earlier. Now, if you don't actually use any assembler programs that allocate storage above the bar, you're probably not going to see GU DSA size or GS DSA size. It'll always show up as 0, but you'll get at least 1 gig in the CICS DSA above the bar. Remember, above the bar, you can have temporary storage, Java runs above the bar, channels and containers are above the bar. And so there's quite a bit of use above the bar, but notice 1 gig tends to be enough, right? It's hard in production environments to see much more than 1 gig being used. So when you get down to the individual DSAs, right? Storage is not allocated contiguously. It's broken up into individual pieces as well, right? So within each of the DSAs, we're going to find that we have these extents, or chunks of storage that are allocated, right? And they're given to the extents as given to the DSAs as needed, right? So for example, if you're talking about the user DSA, which is where most task lifetime storage will live for the average task, you'll see that the extend size could either be 256K, and that's for most of the DSAs below the line, or it'll be 1 meg just for the user DSA below the line if you're running with transaction isolation. But we'll talk about some of these parameters a little later. Above the line in the EDSA, we tend to use 1 meg extend sizes. So we allocate storage in 1 meg blocks pretty much. Now, that doesn't mean you have to get the whole meg. We'll talk about that later. But nonetheless, that's the minimum size. If you have a program that you load and the program is 16 meg, then obviously Kix will get you or allocate you a whole 16 meg chunk. But if you're asking for 100 bytes and there's none, he'll get a 1 meg extent and give you that 100 bytes out of that 1 meg extent, right? So I throw up this chart, but we'll talk a little bit about some of this stuff later on. And that's just to say the control blocks names don't necessarily match the names that we use externally. So for example, you could see I'm talking about the storage manager anchored down toward the bottom of the page, and you could see something called a PPA, or a page pool area. A page pool area is pretty much the same as a DSA. And then you could see the individual extents, right? And so these are allocated chunks of storage that are not contiguous. So the storage within an extent is contiguous, but the storage between two different extents aren't necessarily contiguous. And then you have this page pool map, which is really a way to determine what parts of the extent are allocated or free. So this is my storage manager, how should I say, food map, so to speak, right? This is pretty much what the control blocks look like. I'll mention them individually, although we're only going to focus on very few of these as we look at storage violations. But obviously, if a PPA is a DSA, so you're going to have 4 of those below the line, you're going to have 5 of those above the line, you're going to have 3 of those above the bar. They're DSAs. A PPX is a page pool extent. If a DSA has no storage whatsoever, it won't have any PPXs. If it does have storage, it'll have at least 1 PPX. And again, the storage extents go specifically with the DSAs. And then you have the page allocation map, which shows you what's free or allocated within a piece of storage. If you're suspended waiting for storage, we might see suspend queue elements. And then finally, on the domain level, we could have storage control elements, SCEs, and SCF, storage control free descriptors. And effectively, this is how we manage allocated and free storage within a piece of storage that was given to a domain subpool. So SCA is subpool control area. Now, if it's a fixed length piece of storage, we use QPHs, or quick cell page headers, but we're not going to go into that today because there is no way to manage storage violations within that. So what we're going to focus on mostly is the right-hand side of the picture, right? Because most of the Kix code is good and runs without any problems. We have something called an SMX, a storage manager transaction. There's 1 control block for each task that's running in the system. You can get to it from the storage manager anchor or from the XMTXN, right? The transaction manager transaction has a pointer to the SMX. Within the SMX, it'll show you all the subpools owned by a particular task. And then SCEs are allocated storage, SCFs are free descriptors. So we're going to focus on this bottom right-hand side, task SCA, SCEs, and SCFs, specifically to find a piece of storage. So we'll talk a little bit about domain subpools because they get allocated at the start of a Kix region. They might have different subpool numbers because Kix dynamically allocates them, but the subpool IDs are fixed and they never change. Then we're going to see task subpool storage, and this is all the storage associated with tasks that are running in a Kix system, and they never change. So I'm going to flip out of here for a minute. I'm going to go over to TSO. And of course, my session is disconnected already. So let's get back in here for a minute. Any questions while I'm logging in? Okay, so I'm in an IPCS formatted dump. This is a storage violation dump. I'm running a Verbex DFHPD 730. because this is KICS 5.6, and I'm doing SM equal 1, which is a storage manager equal 1, which is the summary information for storage manager. Now, if you're not familiar enough with IPCS, I do suggest you go back and take a look. I have a presentation on that from one of the older GSE UKs. Now, within the dump itself, you can see that we always start with the dump summary, and I'll show you right off the bat. The message for a storage violation is really great, right? It tells you the region, Apple ID, the TRAN ID, and the task number that detected the storage violation. This dump summary appears at the top of anything you ever go to in IPCS. Now, as I page through this, I just want to show you that within storage management, we start out with what you may have turned on in the SIP, right? So you can see storage recovery, and we'll talk about some of these parameters a little later on, storage protection, TRAN ISO, and I have everything turned on. You can see my current DSA limit. You can see my EDSA limit, and then you can see my grande DSA limit, right? Which is some really huge friggin' number, right? But I only have 1 gig allocated over there. Mem limit is no limit, my region is 0, and that's where we got the mem limit from. And then what will happen is it'll give you a summary of each DSA. Now, in the summary of each DSA, right, the only thing I'm going to show you here is it'll show you the DSA itself, and under it, the extent allocation. But there are some important things right in here I want to highlight. For each DSA, it'll tell you how many times it went short on storage and the time it was spent short on storage. And then storage violations. Does everybody see the 0, right? So this particular DSA obviously didn't have storage violations, even though this is a storage violation dump. And you can see that this has exactly 1 extent allocated to it. So I don't want to go through each and every extent. I'm going to go to the one I want to highlight, which is the user DSA above the line. Look at this DSA, right? The read-only DSA, I can't help myself here, right? The read-only DSA is using 16 mega virtual storage, and you can see how many different chunks of storage it's using, and they are not necessarily contiguous pieces. So here is the user DSA, and I want to point out to you that in the user DSA for storage violations, I can see the number 1. So right away, I know my storage violation is within the user DSA, right? And depending on whether I had storage recovery on or off, right, you're going to find out that obviously the storage area that's violated is in this chunk over here. But I know it's in the user DSA, and later on I'll show you how that's helpful. Now, what I'm getting to here is if I go past here, and I go past all the different DSAs, which you're welcome to look at, you get an extent summary, which will give you the DSA name over on the right-hand side, but it'll put it in contiguous order so you can see that. You'll get the SMXs. Now, the SMXs were too long to spread out on one line, so you could see task number 3 over here, and if you page down, you'll see it again. So this is like an extension. Right? And there's where all the addresses of the actual subpool control areas live, but we don't have to use an address. We can use the eye catchers I'm going to show you later on. So what we really want to get to is this task subpool summary. So this just shows you every task gets storage out of 6 subpools. You can see that for every single task. One of the things you'll see in a storage violation dump, I'll move to the bottom here, is you'll notice that there is a task that only gets storage out of 2 subpools. How is that possible? Well, it's only possible if the task was in the middle of cleanup, which automatically tells me that task 202, which I knew from the message at the top of the dump, has a storage violation, right? And in fact, because one of these areas are still here, I know that the storage violation is in one of these areas. And because I actually know that it's in the user DSA, I actually know that the storage violation is in this area. So I actually have enough to go forward and look at the violated area. But we're going to go through this properly. Now, I also wanted to point out after that, it'll show you the subpool summary, and you'll see all the domain subpools have nice names. And the only time you'd go here is to shift over to the right-hand side. If you're getting a short on storage condition, perhaps you can see who it is that's eating up all your storage, right? So that's just a little overview of storage management. And I'm going to switch back to here and ask, are there any questions? No? Okay. So let's do what is a storage violation. So here are my DSAs. And again, I ignored the ones above the bar because we don't really run anything there yet. And you'll see I drew a line over here between here and here. And the reason for that line is simply because the user DSA cannot run any programs, right? So the loader doesn't even know he exists. This is for task lifetime storage. These DSAs can all run programs, right? Read-only DSA is for re-entrant programs, Kix DSA is for Kix programs, shared DSA is for programs that are non-re-entrant. The trusted DSA, I'm not even going to go through it, it's for security information. Now, where your storage comes out of for a task depends on the transaction's task data key and task data location. So if you use the defaults, task data key user, task data location any, your storage will come out of the user DSA like it did in my dump. It could come out of the user DSA below the line. It could also come out of the Kix DSA if you use task data key Kix. So we already saw some of these subpools, right? Kix allocates 6 for each task, and that's what I wanted to get to. These subpools are exclusive to the task, and you'll see they all start in a letter and end in a task number. Now, what's that all about? Well, those are called storage check zones, as we're going to see. So what is a storage check zone? A storage check zone is an easy way to determine who owns a particular piece of storage, and it lives on the front and back end of every piece of storage. It starts with a letter, and you could see M for macro below the line, right? In Kix storage, Kix storage above the line, below the line user storage, above the line user storage, and then there's the Grande DSA storage. And then it has the task number. But what do we use these storage check zones for? Well, the storage check zones are simply used at the front and back end of any allocation, right? Think of them as license plates on a car, right? They're used to assist in storage violation detection. So basically, Kix has the ability to check the front and back end. And of course, they should be U and the task number, M and the task number, and they shouldn't change. If they change, it automatically indicates that somebody has stepped over the end of storage, or perhaps somebody has written over the back end of another piece of storage and ran into your particular storage area. Now, there's a few notes at the bottom about storage recovery. You could have storage recovery. Yes, Kix can fix the storage and reuse the area, you know, if a violation occurs. If it's no, he freezes the storage and the task, and you could read up all about that, but I wanted to point it out. Now, there are other types of storage violations, the older ones, like for storage accounting areas for old TIOAs. I'm not talking about them in this presentation, but needless to say, they still have 8-byte areas, but they also have a chain pointer, right, which points to the next area. These were dangerous because if you had a storage violation and you overwrote a whole particular area, you could end up with a hole in CICS and the Kix region could come down. But because these are in older areas that have been running like this for 40 years, it's unlikely that you'll see a storage violation in any of these areas. So what are storage violations? Well, this is how I categorize them. There's a simple overlay. Literally, you write off the end of your own piece of storage. Now, you can't protect against that. No one's going to stop you from shooting yourself in the foot, right? But you'd like to know you did it, and you'd like to know what program did it. So you still have to solve the problem, but you can't prevent against these. Then there's the complex ones, where one task will write over the area of another task, right? That's pretty bad, because now you got to find out who it was that stepped on you. And that is possible if you don't have all the storage protections turned on. And even if you do, you can still get some of these. But those only occur possibly maybe 10% of all the violations I've ever looked at will be complex like that. 5% of them are undetectable. This is really bad. This is where we don't actually hit a storage check zone, which doesn't mean it's not a storage violation. It just means that Kix does not detect it as a storage violation, right? And so you might see a transaction abend occur or something like that, and you're going, what the heck is that storage here? That ain't my storage. Somebody else must have overlaid me, right? And then there's the really ugly ones that hopefully don't happen too often, and IBM will help you with those. Undetectable and complex, where you suddenly or somebody suddenly writes over Kix domain storage or unallocated storage. I've seen where it's running for years and nobody's noticed it. And then boom, next thing you know, you get a violation, brings the system down. It doesn't reoccur for 6 months, so it's hard to detect. and it's from code that was written 25 years ago and nobody ever saw it. So I've worked on a few storage violations that have taken me 6 to 9 months to finally resolve. So hopefully you have none of those. So let's just quickly talk about causes of storage violations, and then we'll break it open for a few questions. So some of the causes of storage violations, you could have user programs with incorrect lengths, right? So you could end up in a situation where, you know, you do a get main and you thought it was 100 bytes and you forgot later on and you wrote to it at 120 bytes and you overlaid the end of a storage checksum, right? Or the end of a storage area. Or it could be TWA and CWA usage and sizes change, or TCT user area, or your COM area mismatch because you recompiled a bunch of programs, but you forgot a few, right? Linkage section areas, those types of problems, right? Any program with incorrect lengths can cause storage violation. You could also get incorrect index or subscript values, like a runaway index or subscript, right? Where you run off the end of it because you don't have good ending criteria, right? No editing of index or subscript. So that can always happen to you as well. That tends to be writing off the end of a particular piece of storage. Now, you could also get things like task storage availability, right? What if, you know, you did a free main and somewhere in another program you thought that pointer was still active and you wrote to it and it's already been allocated to another task? Yeah, things like that can happen. You could get an invalid address as a result of some sort of a set failure, and you think it's valid and you didn't test for it properly. And no blaming here, it just happens, right? And next thing you know, you're writing over some other person's storage. Uninitialized pointers is also a good example, right? Or maintaining those pointers beyond limit. So, I mean, it's not everything that causes a storage violation, but they do tend to happen from time to time. You could have some older code, right, where you're hand posting ECBs, you know, for canceled or terminated tasks, things like that. Now, obviously, over the years, the fact that you're running the same applications and hopefully the changes are minimal, it's less likely you'll get more and more storage violations, hopefully less and less. So we're going to talk about protecting storage in CICS to try and minimize storage violations, and then we're going to shoot the dump. But first, I'll open it up. Any questions so far?
None through so far, Ezra.
Okay, good. So let's talk about protecting storage. So the first thing that IBM did, right, is they said, you know what, we can protect storage. Now, this matches some SIT parameters. And as I mentioned, when you go to a particular dump over here, and this will drive me crazy if I keep getting disconnected, but I'm going to do it anyway. If you, so I'm going in and I got to open my dump again, and I apologize. And I go back into the verb exit, right? SM equal 1 is the summary information, right? And if I page down a couple of pages, when you get a dump, right, because you could have a lot of regions in your environment, someone like Rob might have a situation like that where he's not sure what exactly you had turned on at the time. So we're going to talk about things like storage recovery, storage protection, request, and then if it's active, rent pugum protect, tran ISO, right? So these are some of the protections that CICS gives you, but I want you to understand what you get with these protections. So here we go. So let's talk about rent pugum. It's an easy one, right? And in fact, the default is to turn it on. So let's just say if you turned off all storage protection in CICS, what you would get is every single DSA here would run in something called key 8. Key 8 is CICS key storage, which means any program running in key 8 can overwrite the storage. So if you turn off all the protection in CICS, right, what would happen is anyone running in CICS could write to any DSA at any time, right, and cause storage violations. So the first thing IBM did was they said, you know what, this is an easy one. What we're going to do is we're going to create this, well, they didn't create the storage keys, right? There's 16 of them within z/OS. The lower the key, the more protection you get. So what they said was, we're going to make the read-only DSA above and below the line protected. Key 0 is the ultimate key. The only one who can write to key 0 storage is the loader, right? The MVS loader, which Kix uses to load programs, right? And in the SIT, if you say rent pugum protect, this becomes key 0. Now, what does this do for you? This prevents anyone from overriding any programs that are loaded in the read-only DSA. And you saw in my region, I had a lot of storage out of the read-only DSA because most of my programs are reentrant and they run out of the read-only DSA. Notice that with the protection, you get key 0. Without the protection, you get key 8. So I think there's probably very little excuse today to have rent pugum as no protect. Now, obviously, you could have vendor program problems and other issues, but you should try and avoid it wherever possible, right? Now, if you turn on storage protection, which, by the way, the default is also yes, right? So you'd have to actually turn it off if you didn't want it, right? What it'll do is it'll degrade these two DSAs, the user and the shared DSA, out of key 8 and into key 9. And remember what I said, the higher the key, the less protection you get. So it's really not about protecting these storage areas. What it's really about is protecting the Kix DSA above and below the line, right? By making it key 8, because we're going to see that most programs that we set up in the world of Kix run exec key user, right? Why? Because there are application programs. So if we run them as exec key user, it means that if we try to overwrite the Kix DSA, we will not be able to do it because it has a lower storage key, right? And that's where we'll get, you know, an ASRA, right? OC4. And now, if you have those two protections turned on, you'll notice that we protected these two DSAs. The trusted DSA is also key 8, so you'll already see that these DSAs are now fully protected. You cannot violate storage in one of these areas. Now, keep in mind, however, you could still have programs running as exec key Kix, and they might allow you, those programs, to violate these areas, which is why you should have as few of those programs as possible. Now we also have the ability to turn on transaction isolation. Now, transaction isolation came out a number of years ago, and there's always been arguments as to whether or not you should run Tran ISO in production, should you run Tran ISO in development, or both, or neither, right? And it's hard for me to give you an idea of what to do, but I'll show you how it works, and then you can make your own decisions, right? So when you run with transaction isolation, the first thing to understand is isolation is only in the user DSA and only affects task lifetime storage. It has nothing to do with programs running, right? I mean, it does, because everything does, but it literally provides protection to users. So let's see how it works. When you turn on Tran ISO, I want to just point out that your storage footprint will increase. We're going to see that in a couple of pages. So your storage footprint will increase if you turn on transaction isolation, right? Now, the way this works is transactions that are not isolated, right? They have exec key Kix, run as something called base-based transactions. That is to say, because they run in Kix key, their task lifetime storage comes out of the Kix DSA, not the user DSA, and therefore you can't isolate them because we can only isolate storage in the user DSA. So those are always dangerous to have too many of those. Then you have two options. With isolate turned on, isolation in the SIT, on individual transactions, you could say exec key user isolate no, or exec key user and isolate yes on the individual transactions. So how does this thing work? When you say isolate yes, what you're doing is you're isolating a transaction into a unique subspace. Now, what is a unique subspace? Think of it as a jail cell, right? As a jail cell, right? Just imagine you're sitting in a jail cell, you know, I'm assuming it's the same way in the UK, but you know, you got bars up and down the walls and that kind of stuff, right? And effectively, I am not protected from the world. Well, I guess I am if I'm hidden away, but really the world is protected from me. Yeah, I can't get out of that jail cell. But if there were a guard standing outside that jail cell with a gun or a really big rock, he could throw it, hit me in the head, and kill me. So effectively, isolation doesn't provide you with any protection at all. What isolation actually do is protects the world from you. Does that make sense? Hopefully it does. Now, obviously, if everybody is isolated, then they're all in their own jail cells, and it'd be really hard for them to hurt each other, right? There's no rocks in there. They can't pick them up. They can't do anything. So the ultimate is exec key user isolate, yes, but there's a larger storage footprint and there's more CPU overhead for that. So you have to decide whether you want to run it in production or not. Now, there is this concept of common subspace. The problem is when you're isolated, it means that you can't write to storage that belongs to another task. But what if you have these storage violations that were orchestrated or organized into your applications that two applications can talk? What you can do is set them to isolate no, and it's like a shared jail cell. Everyone with isolate no lives in the same shared jail cell. And surely you've seen movies where you have like 15 guys in the same jail cell. That's a shared jail cell. They can kill each other in that shared jail cell, but they still are protected. The world is still protected from them. So unfortunately, there's only one shared jail cell, so there's a limited amount of protection, right? But transaction isolation further limits the amount of storage violations, and they solve the more complex ones where one task can write over another task. Now, one last thing about protection, there's also command protection, which defaults to yes. It checks the first byte of an into area, so it prevents you from using Kix as an assassin, right? So if you do a read into and you pass them somebody else's address, Kix is smart enough with this turned on to know it doesn't belong to you. And it will also work with, set options as well. So a little bit about the internals, and then we'll do some storage violation debugging. So you're probably saying to yourself, oh, when is he going to get to the dump? Don't worry. That part's really easy when you understand the whole background. So let's talk about storage manager internals. So the first thing to understand is when a transaction starts up, an individual user starts to run in an environment, right? We already mentioned that the DSAs below the line, right, get multiple extents, and the extent sizes are 256K, even for the user DSA, if Tran ISO is turned off. So you could see the right-hand side of this picture, the extent size is 256K. But the page size, the size that a user will get to start out is only 4K, right? So allocations are at 4K, and if we need more, we'll allocate more. Now, above the line with below the line with Tran ISO, yes, there's 1 meg of virtual storage below the line given to a task. Now, if you take a look at the page size, however, below the line, it's still 4K. Okay. Now, when we get above the line, which is where most things run today, you'll notice that the page size and the extent size are both 1 meg for an individual user when Tran ISO is yes. So that says that every transaction that runs in my system requires 1 meg of virtual storage. So you see with Tran ISO yes, you have to make sure your EDSA lim is big enough to handle the max task you hope to support. But with Tran ISO no, even though the extent size is 1 meg, each user only gets 64K. So storage-wise, you can handle a lot more users with Tran ISO no. So that's just FYI. But what we care about is whether or not each user will get 1 meg or 64K, as we're going to see a little later on, right? So far so good. Now, we also showed you that each user gets storage out of 6 areas: Kix below and above the line. Kix storage below and above the line, user storage below and above the line, Kix and user storage above the bar. So there's 6 areas of storage that a person gets storage from, right? Now, it's all pointed to you by your storage manager transaction control block, right? But we're going to use eye catchers to find it inside of a dump, right? Okay. Now you can also chain off of the transaction manager transaction to find it, and you could summarize it inside of an IPCS dump with SM equal 1 or XM equal 1. So what we're going to focus on is SCEs and SCFs chained under an SCA. Effectively, an SCA is the subpool control area. If you have a violation, it's going to be in one of your subpools. And underneath the subpools, you're going to see that SCEs point to allocated storage, and SCFs are free storage descriptors. So remember from the page before where I show you could get 1 meg of virtual storage? Well, the SCF, there could be more than one if storage gets fragmented, but SCFs contain the entire storage you have left in that 1 meg, and SCEs are the blocks of get mains that you've done, right? And they show you the address and length, and you could see the address is at hex 14. And I'm sorry, the address is at hex 10, the length is at hex 14. So the only other thing is SCFs are chained in virtual storage order. SCEs, right? SCEs are actually in push down stack order. So if you go to the bottom SCE, right, which has storage check zones on the front and back end, and you work your way up, right, you would see the order in which you allocated storage. And when you look at this, you'll see you're allocating storage out of a page. Will you get a free piece of storage in the middle like I do in this picture? Only if you did a free main, right? So if you only do get mains, you'll see that you allocate exactly the storage in reverse order. So that says it would be nice to go to the bottom SCE and work your way up through storage to see if there are any violations. Now, the free area doesn't have storage check zones on the front and back end of it, but it's where he allocates the next piece of storage and pushes it down onto the stack. So just some notes and we're ready to debug. So the address of an SCE, right, that storage control element that shows you allocated storage, points to the SZZ, which matches the subpool name. So because Kix allocates 16 extra bytes of storage, no matter what you ask for, right, because he needs this 8-byte storage check zone on the front and back end, it means that the SCE points to that storage check zone. Obviously, when you do a get main, you get control of that storage area, the SCZ plus 8, the actual physical area that you want. Now, it's important to remember this when you're looking at trace. If you have trace available, it's the easiest way to solve storage violations. However, you have to keep in mind that the allocated area is off by 8 bytes, okay? So, and remember, SCZs are both on the front and back end. Therefore, the size of a get main will be at least 16 bytes longer than whatever you did. Also, the minimum get main size, I used to do get mains for 1 byte to see what would happen. I used to get exactly 20 bytes because I'd get 8 bytes on the front end, 8 bytes on the back end, and the minimum allocation that Kix could do was 4 bytes. Well, today the minimum allocation is 32 bytes. So he'll never give you less than 32 bytes, no matter what you ask for. So you get 16 bytes, even if you ask for 1. Now, again, there are no chains in the SCZs like SAAs, so there's nothing to break when you step on stuff. That was the problem with old SAAs. You could step on yourself. Yeah? Now, Kix checks virtual storage on free main or end of task. So that's the first thing you should pay attention to, right? So when do we check for storage violations? At end of task, right? So that's the first problem you're going to run into. So the guy who violated you could be long gone, right? And that's why trace could be very helpful in finding the problem. But we're going to show you some ways to help you if that's the case. Now, the transaction itself may or may not abend. Just because you had a storage violation doesn't mean the transaction is going to abend. Maybe it runs to completion and then somebody finds a storage violation afterwards. In that case, the transaction will complete successfully, believe it or not. So the other thing to look for, right, is whether or not the transaction successfully ran or it abended. If it abended, believe it or not, looking at that dump could be a lot easier than looking at a storage violation dump sometimes. So just keep that in mind. If the transaction ended normally, then you're going to have to look at the storage violation dump. If it didn't, you might look at the transaction dump first, and that might give you a better idea and not have to look through a whole system dump, right? Now, what is a storage violation? Again, the SCZ on the front and back end don't match. So here we go. Ready for the analysis? Any questions before we start this?
No, still all clear. That's real. Keep going.
Yeah, I'm just wondering, is it because I've lost everyone? No, I'm kidding. Here we go. Okay. Now these are kind of the notes that you can take away as well. Sorry, but I'm disconnected again. These are the notes you can take away as well, but we're going to follow through the notes anyway, right? just to make sure you understand what we're doing. And we're going to go back into our dump, but I will tell you what I did. It turns out I had a very big trace table, and because of that, searching through the trace table could be quite hard to do. So what I did instead was I ran IPCS in batch. So I want to show you this. If you take a look in my JCL library, and if you look at the IPCS presentation I've done before, and that's the wrong JCL library, sorry. I had it here. There it is. I have these IPCS jobs, IPCS1, right? And what does IPCS1 does? It runs IPCS in batch, and it runs the verb exit. And this is the first one, verb exit, DFHPD 730, TR equal 3, TRS equal exception, right? So I'm asking for trace level 3, and I'm only looking for exception trace, okay? So that produced this right here. Oh, sorry, just browse it. So I'll just show you, if you page down, you can see it was TR equal 3, TRS equal exception. And again, I find going through IPCS looking at trace is a little bit difficult to do. Why? Because he has to page the whole trace table in, and if it's quite large, it can take some time. And so I just did it in batch to make the session go quicker. You could see this is an SMO 102 dump, right? So this is a storage violation. And I said, what you want to do is find the last exception, find something like exception exe asterisk for 15, right? And it'll take you to the full trace exception entry, right? And so you can see, oh, I should have done last. I didn't do last, Ezreal. So I'm sure the notes say to do last. Let's do it again. And now add the word last. There we go. Storage check fail, right? So going back to the notes, it says a simple internet search will show you that trace entry, right? So if you take a look here, the trace entry we're looking at is an SM0F0C, and you have these items 1, 2, 3, 4, right? You see them all over there. And again, I should have used a wider screen to show this to you, but I'm not going to switch now. I'll just switch back and forth. And effectively, he says that you get in item 2 the address of the storage element that was violated and the length of the area. And so if I switch back over here, you can see the address and length in item number 2 and 3. Sorry, there they are, 2. So my address is 227-04120 for length of 8 Charlie 40, right? Then what he gives you, which is quite fascinating, is he'll give you the first 512 bytes of the storage area, the last 512, and then the data preceding the areas. So always take a look at items 4 and 5 to see what area was violated, right? So if you take a look at item number 4, you can see, I don't see a storage check zone on the front. That's not good, right? So I know my front end storage area was violated. But if I look at the next area, right, the back end one, and I go to the bottom of the back end one, would help if I would have used a wider screen. Sorry. If I go to the back end of the storage area, there it was. I'm sure this is where it maps out to, right? You see the U000202? Right? And that's the preceding area. So I'm showing you the preceding area. What is the point of doing this? You can't turn off exception trace, so you'll always have exception trace. So you'll always be able to do this. Whether you have trace turned on or not, you can't turn off exception trace. So the first thing it'll give you is this. This is the storage check zone that was violated, right? So this tells you right away the subpool control area you need is in user storage above the line, which you already saw when I showed you a little bit about it before, right? We knew it was the user DSA that was violated. So it tells you exactly where that area is, okay? So switch back to the notes for a minute, right? So that's what we're saying here. Find the storage check zone that was violated. Now, if you remember, I did the verb exit and I showed you the dump summary already. You can see that the Tran ID was pay 1, the task number was 202, the region was FUW-FWAR. So you get a lot of good information, right? And we found the exception entry, which in our case was 0F0C. There could be other types of violations, right? So the dump summary is normally the first thing we go to, but we already did that for you guys. Now, once you're done with that, I suggest another trace, right? And this is only if you have trace turned on, which I did. And if you have this as well, this becomes the easiest thing to do, right? So if you have trace turned on, which I did, and I'm going to go into this one. If you have trace turned on, then one of the things you could do is use selective transaction trace for task 202, just to see if you can find the get main associated with the violated area, right? So if you remember from earlier, we're looking for an address of 227-0412, and he said 0. Why did he say 0? Because he's pointing to before the storage check zone. So the way I do this is I always search for the address without the last byte. So this is exactly what I would do, right? I'd go in here and say, find 227-0412, was it? There we go. Yeah. So I can see that. And if I hit PF5 again, I get bottom of data reached. So I did this in abbreviated trace. So you guys can see I found the get main. This is the get main that was associated with the violation. I shifted over to the right-hand side and I took a look at this number right here. And I'm just going to copy it for myself. Okay. Then what I did was I ran full trace, TR equal whatever, 1 or 2. Let's see what we did. I think it was just TR equal 1 to get every trace that was going on, right? Yeah, TR equal 1. Everybody see that? And then what I said was find this. Now, why am I doing this, right? Well, remember one of the types of storage violations was you violating yourself. And I'm really hoping we violated ourselves, because if we violated ourselves, we can easily solve the problem by ensuring we discover which programs we're running, right? So there's task 202. Now, if I page through this, do you see I'm only looking at the left-hand side? I see task 202, and what I'm looking for is the exception that says storage violation. So far, the only thing that ran was task 202. Now we switch to task 0003, the socket listener task. That's a well-known task, right? And so it's IBM's socket listener. I doubt he did the violation. Then I can see a low task number of task 56. I could look up and see what task 56 is in a moment, but I've done that already to save time. And it's another system transaction like a CSSY. He obviously didn't violate me. I'm looking for tasks in my numbered range, right? And obviously my region wasn't running for very long when I took the violation, right? But I'm gonna page through this and I'm looking, as I look through this, for the exception. Now, I will tell you that when I did this, I didn't find any other tasks running except 202. And then I got the storage violation coming up somewhere. I must have passed it. Oops. There's a nice table at the end of this that shows you everything that was running. There we go, storage check zone. So I passed it, it was a few lines up. So if you page from the exception to the original get main, it was only task 202. What does that tell me? I shot myself in the foot, okay? So I know that's what happened in this particular dump. Now, because this was detected at free main time, right? Because this was the task end, and I can prove it to you, you'll notice that if we back up, here's task 202, and task 202 is releasing storage. He's ending. And in fact, as part of the ending of a task, we switch out of our task number and back into the transaction manager that's freeing up all of our storage. And while he was doing the SMAR release storage, right, SMAR, that's where we got the exception, right? And there's the exception address, and this is before the storage checksum, okay? So I know that this task completed successfully, so I don't have a transaction dump to look at. If this was a storage violation detected during free main processing or some other time, then some other domains that provide interesting information is the AP domain with the task ID. Will show you some information that might be useful. The program manager, right? The program manager shows you the link stack, right? All the programs you link to or loaded. The transaction manager is also pretty interesting, right? For an individual task. And XM still exists for the running task, but today he doesn't have much information. All he's going to show you is the storage manager transaction itself as well. Okay, so now the ultimate, right? So now you know it was yourself violating yourself. You could look through Trace if you have it, and you'd only be able to find it with Trace to see what programs were running to identify possibly which programs violated yourself. But how do you actually find the violated area? And that's what this page goes through. You can read through it while I show it to you live. So to find a violated storage area, you do verbx dfhpd 730 SM equal 3. So you need the detailed information for storage manager. Why do you need 3? Because we're going to look for subpools. So we already know we want to find, quote, the subpool control area dot U00000202. Why? Because that's the storage check zone, and you want to find all the SCEs and SCFs, which are chained after the SCA. So when you do that find, there's the SCA. Everybody see that? And then you could see under it, there's an SCE, there's another SCE, there's another SCE, and then an SCF. So I had 3 allocated areas and 1 free descriptor. And remember, I said this is a push down stack. So does everybody see the start of my 1 meg area, 227.0.0.0.0 for a length of 3.00? And then the next area starts exactly after the last one for a length of 420. And the next area starts exactly after the last one for the length of 8 Charlie 40. Now, if you remember the address and length, this is our violated area. So the easiest thing to do is right in the middle of IPCS is do an IPCS list for this storage address. C, Control V, for a length of hex quote 8 Charlie 40. And you'll see the top end storage doesn't have a storage check zone, but I always max to the bottom because I put in the exact length, and you can see the back end storage check zone. So because I know this area was violated, my next question is what was the area before it looked like? All I have to do is hit PF3. I'm back to where I left off. I type in a retp. I pull up that IPCS list command again, and then I change the address to this one, 3.0, for a length of 4 Charlie 0.
Ezra, just be Mr. Grumpy and that you know there's a couple of minutes left.
Okay, I'm almost done. So you guys can see the storage check zone on the front end is healthy. The storage check zone on the back end is where we wrote over the end of the storage. So actually, we want to find out the type of storage this is, and I'll tell you it's a COM area, right? So it wasn't that big of a deal, and somebody wrote off that end of piece of storage. So if you can figure out the data in the violation, you could see where the violation occurred between 2 pieces of storage, you're good, right? Because then all you have to do is find the corresponding get mains, the programs that ran in between, and you're all good. Now, if you're not happy with the fact that task ends and then you get a storage violation, you can run the storage violation track known as CSFE, right? And CSFE will check storage before and after every get main. There's a lot of overhead, but if you're having trouble solving the storage violation, this will allow the violation detection from kicks to get the violation a lot closer to where the violation actually occurred. And it's helped me solve some problems. Some of the messages come out looking slightly different. So as Rob pointed out, I'm just at the end of this. Storage violations are the most common failure type still in Kix. This should give you some idea of how to find the violated area if you have trace, finding the get mains and free mains, a little bit about how storage management works. And now I'll just open it up for questions. Any questions?
We've got nothing actually in the chat, but if there's anyone particular, raise your hand and we can unmute you. Or we can give you a virtual round of applause, Ezreal. That was a hell of a roadmap through there.
Right. Yeah, it's a lot to do in one hour, but the notes are there. So anyone who felt that the end was a little bit quick, believe me, finding the area and doing that work is actually the least about it. You got to really understand how storage management and some of those control blocks work. And if you just get a storage violation dump and you step through this presentation, people have told me it's been a lot easier to solve those problems.
Thanks, Ezra. I think there's a lot to go through there, but like you say, having those notes and a dump in front of you and following things through, doing that a few times should give people a lot of confidence to use the information that you've given us here today. And I'm very grateful for that. I know we're starting off at 9 o'clock tomorrow, but I've been a bit slack because I've been listening to you and worried about the time. I'm not quite sure who we're kicking off with.
Anthony,
I think it's APIs.
Yeah, and
so that'll be ZOS Connect related, one might think.
And when does that session start?
That's at 9 o'clock UK time tomorrow. Yeah. So you'll be fast asleep.
Yeah, I have to get used to it. This is the week where, you know, there's 4-hour time zone difference versus 5. There's 1 week out of the year, and you guys always make GSE that week, which is great when you're traveling there because I have less to recover from. But, you know, it's just something you have to remember because you're only at 3 p.m. there right now, right? Yeah. Whereas normally you'd be at 4 when at my 11 o'clock. We don't change the clocks till next Saturday, and that's when we catch up. So we're always a week behind.
We keep threatening not to change them anymore. And that was one of the benefits of Brexit, totally touted, but I don't think the government's brave enough to do it.
Yeah. No, it's all good. It's all good.
Yeah. Oh, I see Mark Jones has raised his hand.
Oh, okay. Sure.
Just ask him to unmute.
Yeah, unmute.
Mark, you're unmuted. Have a chat.
Assuming Mark has a...
We've scared him off.
Yeah. Is that talk of Brexit, Rob?
Okay, well, maybe if there's a question, it might come later on.
Yep.
Everything's been recorded. That's the last Kix session for today, but there are many other GSE sessions. Mark's having trouble with microphone access.
Did you want to write a question, Mark? I'm happy to answer it for you. We're all waiting with bated breath for Mark to type in a question.
How do you keep
it's the Zoom disease, you know?
Here we go.
Please.
Here it comes.
Did you catch that?
Yes, he says we are reliant on app progs to recognize the storage area. Yeah.
Are we reliant?
Are we?
Oh, yes. Well, yes and no. You're not always reliant. I mean, sometimes it's intuitively obvious, but I'd say 95% of the time, yes. They have to be able to either recognize the storage or if you have trace running. So if you tend to run into problems, I suggest running with a little bit of trace. There are minimal elements of trace you can turn on so that you can at least see get mains and free mains and what programs are running when. So you could determine number one, is it transaction overlaying another transaction, which is unlikely, but it's still possible. It's usually you overlaying yourself, and then you could see all the programs that got control. Once you know all the programs that ran and no other transactions ran from the time of the get main to the time of the storage violation, you know it has to be one of those programs. So you literally go back and say to the app programmers, look, if you don't recognize the area yourselves, you're going to have to go forensically through X number of programs. And I usually give them the names of those programs because you could see the loads and you could see the links or XCTLs. And I give them the names of the programs and I tell them, look, one of these caused a storage violation. Go ahead, go to it. Yeah. But yes, it is frustrating because you're relying on them to recognize the storage area. No question about it, right? If it's not your application, how would you know what it is? But you'd be surprised if you actually show them the area. 90% of the time, I find they actually do recognize it if they remember what the application does. But other than that, yes, yes, it can be frustrating.
Okay, well, I've got kind of a question and kind of a debate. You'll find it a bit, probably a bit awkward. We touched on transaction isolation in production earlier on. Now,
Yes.
my take on it is a bit old school because I used to run a lot of boxes, didn't have a lot of MIPS, that it's a bit of an overhead. And you can switch it on in test and get most of the coverage you need if you've got good testing.
Yeah.
But there's always a risk in production. And if you're very risk averse, like a big bank, like we are, then switching it on, although it's an overhead, might help you avoid the odd outage.
Yes. Yeah, I've had that discussion with many people over the time, right? And I will tell you, it's really hard to, predict. So what I find most customers will do is they'll probably run it in development and they'll make sure to test the production regions that they're capable of running it. Because if they get the various odd storage violation more than once in a region, they'll turn on transaction isolation. But remember, it doesn't necessarily solve the problem. It won't stop you from violating yourself. So it's only if somebody violates you. So I have one customer that's what they do. They make sure their regions are capable. If they get a storage violation more than once, they will turn on isolation in that region. And I would say maybe 5% of the time that helped. It doesn't usually help either, Rob, because it's usually you violating yourself, right? So that's been part of the problem I've run into.
Yeah, for sure. And switching it on if you haven't tested everything in your regions and you've got a lot of legacy code can be quite a scary proposition,
right?
Because you could shoot something in the foot that legitimately, or as part of the normal way it does business, is updates somebody else's storage.
Yep. Absolutely. Yeah.
So
I don't disagree with you. I run it in development.
Yeah. Is how much of an overhead is it? And I've heard all sorts of figures bandied around between nothing and 10%.
Yeah,
I don't know what the answer is.
I've seen
Depends
12.
on your workload.
Yeah, it depends on your workload, but I've seen about 12, right?
Okay.
But I've heard other organizations that see half that amount. So it really depends on your workload. You have to turn it on to see what it'll cost you to determine whether you want to turn it on or not. You know what I mean? So as Nick will tell you.
No, thank you very much, Ezra.
Well, thank you guys, and I'll see you in a week's time for the next one.
Yeah, see you next week, and we'll look forward to it. Cheers,
Thanks,
Ezra.
everyone. Cheers.
Cheers, everyone.
Bye.
Bye for now.